Oh, we don't want the munchkins to be recorded. Okay. All right, so this is, I think, lecture 7 of probability. Does that sound about right?
Sounds right.
Sounds about right. All right, so the goal of today is to talk about programming. I've got a couple of problems that I find interesting that have good coding challenges to it, and so I'm going to show how to do this in Mathematica. Why am I doing this in Mathematica? Yes?
Because you learned to use it early and it has a lot of built-in functions.
No, more because I learned to use it early. If you just stopped then, you would have been fully right. It does have a lot of built-in functions, which is nice, but it's really because I learned Mathematica first when I was in college in physics labs. There is a huge loyalty to whatever you learn. This is why a lot of companies, they want to get you to sign up because they know people won't go through the hassle of switching. So the code I'm going to show you, the specific commands will work well in Mathematica. They won't work in other things. If you want to look in other languages, it's not that bad. One thing that's nice in Mathematica is if you do a question mark and then start typing the word you want and then do Shift-Enter, it will open up. Let me bump up the power so it runs a little faster. And it will list, here's a bunch of commands. And then if you hit the double arrow here, it will open a new window which will explain how to use the command, have a bunch of features down here. So when you're coding, this is a really useful item to have. The other thing which I frequently do when I code is I have two windows open. The window for the program I care about and a window to just test something and make sure I'm coding it correctly. I've programmed in far too many languages, and I often forget, now what is the syntax in this language versus this? Do I have the double braces here, the single braces here? I don't always remember. If you have a second window open, you can just check it there. Okay, so in terms of things to do, I thought one nice thing to do might be, we did the roulette problem, right? So trying to calculate what's the probability we have 5 consecutive blacks. Okay, so this is a pretty good program to write. So 5 consecutive blacks. And it's going to be a function of the number of simulations we want to do and then the number of spins. So you use an underscore in Mathematica to say that that's a variable. You try to have good descriptive variable names. X and Y would not be great variable names here because when I look down, I can't really tell what they are. A lot of languages like Mathematica have tab completion, so when you start writing something that it knows, it will fill it in. I'm calling this 5 consecutive blacks. I could have, of course, had the number of blacks be a variable as well. I'm going to assume that the probability of a red is 1/2 and the probability of a black is 1/2. Could I have made that another parameter? Sure, I could have had that as a parameter p as well, and so I could have put in, num black if I wanted to, and p, and just made this a more expansive program. Right now, I'm just trying to give you a sense of what's going on. So you write module in Mathematica to mean that you're doing a program. This means I'm not having any local variables. I'm being lazy. So any variable I do here, its value could actually be seen when I'm done. All right, so num is going to be the number of trials we're going to do. Num spins is the number of ones in each trials. And let's set success equal to 0. So success will be having 5 consecutive blacks in num spins. And then you use parentheses, star, star, parentheses to mean a comment. For those of you who program well, you should have been told numerous times to always comment your code. It is never a bad idea to comment your code extensively. Frequently, somebody else will have to use the code years later. I know some people don't like to comment their code so that they are now indispensable to the company. That's really not the right attitude. You may need to look at your code in a year or two and you may not remember what you were doing or that there was a subtle issue. So I'm going to have num successes be 0, and every time we get 5 consecutive blacks, we'll call that we'll increment by 1. So I'm going to do for n equals 1, n less than equal to, and it's going to shorten that into the less than equal to sign, less than equal to num n plus plus. And so this will start the for loop. So our curly braces begin, another curly brace is an end, and I'm going to write end of for loop. For those of you who haven't programmed much, it's a good idea to start and end immediately so that you don't worry about where things go. Put comments to say, I've now just ended the for loop. Okay? So now what I want to do is I want to do 100 spins. So what I'm going to do is I'm going to have my spins. I'm going to initialize this to be empty. There's lots of different ways of doing it. And then for s equals 1, s less than equal to num spins, s plus plus, spins equals append to spins, and then I want to do random, and that will give me a random number between 0 and 1. Well, I don't really want a random number between 0 and 1. I want either 0 or 1. Right? So then the question is, how do I get a random number between 0 and 1? Well, let me open up another notebook. Let me do random 1. Let's see, how is that? And so now I'm forgetting, oh, what is the command? So let me just look up the command for random. And one of the things we saw when I was typing is there's something called random integer. Oh, that could be useful. And this gives a pseudo-random number in the range I min, I max. Oh, so if I do random integer 0, 1, that should give me either a 0 or a 1, 50-50. And I've just tried it a few times. Yep, that seems to be working. So I'll do random integer 0, 1. And now I close the brace there. I close it here. And now I've created a list of 100 spins. I don't necessarily have to make a list of 100 spins, but this way it's convenient. It's all there. If I want to do other things, it's there. Is s a good variable name? All right, so I see somebody shaking their head no. Why is s a bad variable name?
Because you don't really know what it means. You could have multiple things that start with s in this.
So there's multiple things that could start with s. Here, it's not horrible. It's coming from the word spins. There's another reason why s is a really bad variable name. It's more so when you're writing than when you're typing. Yes? Like a 2? Like a 5. It looks like a 5. So if I was writing, I would never want to have s as a variable name. It's very easy to have that amalgamated into a number. So what I'm going to say is initialize list to empty, put in 100 spins of 0 or 1. And now what we want to do is we want to check and see, do we have 5 consecutive heads? So how can we check and see if we have 5 consecutive heads? So, or I guess black. 1 is black, 0 is red. So what would be a way to take this string of 100 spins and quickly see if we have 5 consecutive ones anywhere? Yes?
Is there a substring function? And you could check for the substring 5 ones?
So one possibility is if we have really good language, we could actually do something such as check and see if this substring occurs in this string. And Mathematica almost surely has that built in. It has a lot of really good string functions. So that would be an excellent way to do this. There's another way to do this which I really want to emphasize today. There's a reason I'm calling things 1 and 0 instead of R and B. Yes?
Can you check to see if the sum of any 5 consecutive numbers is 5?
Good, I can check and see if the sum of any 5 consecutive numbers is 5 or the product of any 5 consecutive numbers is 1. Either one would work. This is similar to how when I've talked about Sudoku, make the numbers not 1, 2, 3, 4, 5, but make the numbers 1, 10, 100, 1,000, and so on. And then you can just check things very quickly. So what I would want to do is and now let's see, so what we've got to do is we want to march down. So we need like a local variable, 5 in a row equals 0. And then for k equals 1, k less than equal to, what's the last one we would have to go through? Yes? 96. So is it 96? Is it 95? There's a little bit of a question mark in this. So it's how you want to start. We could actually start, we were going to go from k plus 1, k plus 2, k plus 3, k plus 4, k plus 5. So if we start like that, maybe I want to start k equals 0. K less than equal to 95. And if we do k plus 1, k plus 2, k plus 3, k plus 4, k plus 5, when k is 0, we get the spins 1, 2, 3, 4, 5. And when k is 95, we get 96, 97, 98, 99, 100. Yes?
In Mathematica is the first,
The first entry in a list is 1.
it's one.
Right? When you're calling about the entry in a list. And again, if you're ever not sure, just check something. So k goes from 0, k less equal to 5, k plus plus, and then if the sum, and now it's going to be spins, and I want to pull out the element k plus j. J goes from 1 to 5. And if that sum double equal sign equals 5, then I'm going to say 5 in a row equals 1. And if not, I'm going to do nothing. So let's see what's going to happen. So I'm going to do this basically 96 times. And what I'm going to do is for each time, I'm going to look and see if the sum of spin k plus 1, k plus 2, k plus 3, k plus 4, k plus 5 equals 5. If that happens, the only way that happens is if I got 5 ones in a row. And if that happens, I make 5 in a row equal to 1. If that doesn't happen, I don't make it equal to 1. Yes?
Shouldn't the upper limit on k be num spins minus 5 instead of 95?
Oh, yes, you're right. That's right. I'm assuming it's 100. You're right. It should be num spins minus 5. Thank you. Because we're trying to do it for a general number of spins. Thank you. Now, this is a little bit inefficient here. As soon as we have 5 spins in a row, we should break the k loop. Right? Why should we keep looking? So what we could do is we could make this a little bit more efficient. And then if we happen to have a sum of 5 in a row, so now I might have unfortunately put things in the wrong spot. Okay. So this is end of k loop. So as soon as we have 5 in a row, why should we bother to continue to check? So what should we set k equal to if this happens? Yeah, num spins. Or if you want to even be safe, num spins plus 1. It's now outside this range. So as soon as we get 5 in a row, we break the loop. There's slightly faster ways you could code this, but this is not bad. All right, so now what we've done is we've gone through this. And now what we can say is if, let's see, what is it? What are we calling this as? 5 in a row equals 1, then we want to say success equals success plus 1. And I'm just a little bit worried if everything is arranged properly. Because this is slightly more indented here, so I'm worried that I have a mistake somewhere. Doesn't seem to be giving me a mistake. I'm sorry? So this if statement? Oh, maybe I didn't close that down. I think you're right. So let's see. So let's break this up a little bit. So if this wait a minute. I think is this the end of the if statement right here? Okay, so this is end of if statement. And then did we now miss the end of the case statement? All right, so let's see, where do we make a mistake? So if sum spins equals 5, then, okay, over here, and this is the part over here, and then this ends the if statement. Okay. I think that's right now, and everything looks like it's aligned properly. Oh, this looks a little bit bad here. So, all right, so let's see. So here's the start of the if. This is the end of case statement. Okay, so we've definitely got the case statement closed. Now we've got the if statement starts here, and so let's see where the if statement ends. End of if. And we've got the end of the for loop over here. So, all right, so this is bad. All right, so for k goes from 0, we've closed off the k statement here. If starts here, if ends here. So now we have the sum and this closes off the sum. So if the sum equals 5, then we want to do the following things. 5 in a row equals 1, k equals num spins plus 1. And then that will end that. All right, so sometimes when it gets like this, let's just back up a little bit. So this ends the for loop, this ends the module. All right, so let's go back. So we've got the for loop here. 5 in a row equals 0. For k goes from 0, k less than or equal to 5. So we've ended the k loop here. Okay. Oh, so is it? Oh, maybe it was the end that we were supposed to end. End of end loop. Okay, is this working now? So let's try this. So 5 consecutive blocks. Let's do num is 10. Let's do spins is 100. Okay, so it looks like it's correct. I'm just not quite sure why this is putting this in purple, other than we're at Williams College. So that's just throwing me a little bit as to why that's in purple. Yeah, all right. All right, so for k goes from 0, k less than or equal to num spins minus 5, k plus plus. Let's just do this, the longer code. And then we'll do if the sum of spins k plus j, j goes from 1 to 5. If that equals 5, then we'll say 5 in a row equals 1. And then we've ended everything. And then if 5 in a row equals 1, all right. So I think I'm just being thrown because it's displaying this in purple. I'm not sure why it's displaying this in purple. All right, so if 5 in a row equals 1, then we increase success by 1. And now all we need to do is just print the output. Print. So what we want to do is we want to do success times 100.0 divided by num. Okay, and so now what I'm doing is I'm running it 1,000 times, and the answer is quite small. Let me make it a little bit larger. And we're getting 82.3%. And so I said that the answer is around 80%, so doing it 1,000 times, it's not a problem at all. If I wanted to do this a couple more times, it's going to take a little bit longer. And this is where you start getting frustrated. You know, how long is it going to take this program to run? So what you can often do is, if you want, is you can put the phrase timing around your command. And when you do timing, it'll tell you how long the code takes. Now this part I've got frustrated, so I'm going to just abort it. Let me do it, 1/10 as long. And then that should run pretty fast. The other thing which is worth doing in just some codes like this while it's running is a simple statement. Okay, now it finished, and it told us it took about 7.7 seconds. You can put in a little bit of a command so that it outputs where you are. So what we'll do is if mod, let's say n, and then we'll do the number we want to do divided by 10 equals 0, print we have done, and it'll be 100 n divided by num, and then %. So this will print out basically every 10%. And so now when we run, you can get a sense of where you are, is your code almost done? It's very worthwhile to put in a few lines like this to just get a sense of how long it's taking. To do a small simulation first and get a sense, okay, it's taking me about 8 seconds to do 10,000. If I want to get up to 1,000,000, how long is that going to take? Do I have to be more efficient with my code, or is my code good enough that there's no problem? Okay, any questions on something like this? So this is real simple code to get something of, what is the probability of getting 5 consecutive blacks? If we change the 100 to the 200, and now we do 200 spins, and it was 80% with just 100 spins. How good is it going to be with 200? Now, one thing that we're doing is we're just printing what percentage we've done. We could also print out what percent of successes we've had up to this point, so that if you have a system crash, you would at least get some information. So you want to get into good programming tricks. And so here, it's 96.44%. So with 200 spins, it is extremely likely that you have 5 somewhere. Okay. For the next set of problems, let's go and do some poker problems. Let's try to calculate the probability we have at least 2 kings and at least 2 queens. Any thoughts as to how we would do that? So at least 2 kings and 2 queens. And we'll do num for the number of simulations we do. So I'll start off the same way, module and module. So we have 52 cards, ace, deuce, 3, 4, all the way up to king. And I have a hand, and I want to see, do I have at least 2 queens, at least 2 kings? So what are the possible hands? So what would be the possible hands that would succeed? Give me hands that would have at least 2 queens and at least 2 kings.
Full house.
Okay, so full house, which would be 2 queens and 3 kings, or 3 queens and 2 kings. Anything else? 2 queens, 2 kings, and a non-queen or king. So we want to go through and we want to form hands and we want to check and see, do we have at least 2 queens, at least 2 kings? Anybody have an idea on how to do that? I don't care if it's a bad idea, I don't care if it's a slow idea, just give me a way to code. You can use advanced string theory functions, and this is different than what the physicists would say. How could we check and see if we have at least 2 queens and at least 2 kings? Yes?
You assign the kings and queens the value of 1 and all the cards value of 0, and see if your hand is the value of 4 or higher.
Okay, good. So we could give kings and queens the value of 1 and everything else the value of 0. The problem is, what if I have 4 kings? That would get a value of 4, but I would not have 2 queens and 2 kings. You're on the right track. This is much better than saying, let's have the symbol Q for queen, K for king, and check and see if we have at least 2 Qs and at least 3 king. Yes?
Going off of that idea, maybe we can make the kings like 0.1 and then queens 1.
Okay. So this is Williams College. We are not allowed to discriminate on many categories, but we are allowed to discriminate on non-integral status. So we don't like to work with fractions. So instead of doing something like 1/10 and 1, what should we do?
Like
10 and 1. Right? We like to work with integers. It's much nicer to work with integers. So let's have a queen be 1 and a king be 10. So now the hands that work, they would have and everything else is 0. The hands that work, they would have a sum of either 22, 32, or 23. Right? So that's all we have to do. So now what we can do is the following. So we're going to make a list. And I'm going to start the list to be 1, 1, 1, 1, 10, 10, 10, 10. So actually, let's call this not list. Let's call this the deck. This is our deck of cards. And now what we'll do is for k equals 1, how many more cards do we have to add to the deck? (44). K plus plus, deck equals append to deck 0. And so now queen equals 1, king equals 10, rest equals 0. And so we don't really need finer structure of the cards. All we need to know is it a queen? Is it a king? Is it something else? Now, if we wanted to do another problem after this, this would not be great code. But if we want to just do this one problem, it's much simpler. So now what we want to do is we want to do a random sample. All right, so I go back over here. Are people able to see in the small type? So if I do like random sample, can people see this? So maybe random sample might not be right. Random permutation. So it gives a list of n pseudo-random permutations. So maybe it's sample. All right. Random choice. Okay, so let's see. So we do random sample. So it's a list of all subsets. I don't want all subsets. It should be like a random permutation. The command should have been random permutation. Oh, okay. Oh, maybe just the way it's writing it. So let's just test it. Random permutation. 1, 2, 3, 4, 5. Let's take 3 elements. Nope. Random sample. Okay. So the command is random sample. All right. So this would give me a random set of 3 elements. Another random set of 3 elements. So there's a lot of good commands there. And the point is, if you're not sure what you want, don't panic. Just keep question marks. Look at the things. Check the different codes. So we want random sample. All right. So now I come back over here, and so now we'll do for k equals 1, dec equals append to. I'm going to close off the k loop. Okay. So now for n equals 1 and less than equal to the number we're doing, n plus plus. And this would be end of n loop. And then we should probably have a variable that will keep track of the number of success. So let's let hand equals random sample from the deck, and we'll take 5 cards. So that's all we need to do. So on any poker problem we want, this is now going to be the code we'll need. And now what we need to do is if the sum of the cards in the hand, I goes from 1 to 5. Well, here. Let's let value equal the sum. All right. So we've now just set the value to be the sum of the cards in the hand. So now, if there's probably better ways to code, but if value equals 22, or value equals 23, or value equals 32, or anything else could work? Or is that just it? That's it. So if any of these happen, then success equals success plus 1. And then print 100.0 times success divided by the number. So at least one working. Let's do 10,000 hands. And it's saying that the answer is about 0.8. and did it pretty quickly, so we'll do 100,000, 0.6. That's pretty fast. So we can do, a million without too much trouble. Do you expect that this is correct? This is a very low probability. I'm multiplying by 100, so this is the percentage. This is well below 1% of the time. Okay? So you can actually calculate and see if we've made a mistake. What if I wanted to instead change it, so instead of having at least 2 kings and at least 2 queens, what if I wanted just at least 2 kings? How would we change it so that we would calculate if we have at least 2 kings? What would we change it to? Yes? Okay. Yes?
If the value is above 20.
So why if the value is above 20?
Because the tens place is a number generally like how many kings there are.
Right, so the kings is coming from the tens place. So to have 2, you were doing it from the queens. It's really the same. So if the sum is either 20, 30, or 40, or higher, the only way you can get a sum of at least 20 is to have 2 kings. Even if we had 4 queens, that would only give us a 1. So all we would have to do is say if value is greater than or equal to 20, then success equals success plus 1. And now that will give us the probability of having at least 2 kings. And so that's about 4.1%. So it's really easy to do a lot of these problems when you have some kind of programming language like this. And then depending on what you want to do, you assign different values to different cards. You want them to be well enough separated so you can do a lot of tricks like this. Okay, so I'm going to remove this and just restore it to the original problem. And I will just put some comments around this. This would do at least 2 kings, queens free. And over here we'll say if sum is 22, 23, or 32, have at least 2 queens and at least 2 kings. Okay. Any questions about this one? So another one we did was the permutation problem, correct? And so let me just keep the text size large. So what was the probability of a derangement? Anybody remember? That when you reorder the numbers 1 through n, yes. I'm sorry? I don't think it was e minus 1. It was close to that. Well, e minus 1 is larger than 1. So we know that that's got to be a little bit off. Oh, e to the power minus 1. Yes. Yes. So 1 over e was the probability of a derangement. So what's nice is this is something where we remember the theoretical answer. So we want to calculate derangements. So we'll call derangement. We'll do maybe the size, and we're going to do the number of trials. And then success equals 0. And then in the end, print 100 success divided by num. So we'll do this like this. Observe and then we'll do print predict, and then it should just be 100 divided by e. And so we'll do that at the end and just compare. All right, so we want to calculate the probability of a derangement. What is the simplest way to check and see if we have a derangement? Well, let's start off with our list as before. So list will be empty. And then for n equals 1, n less than or equal to size n plus plus, our list equals append to list and then our number n. So this will generate a list. I'll use the letter S. I want to use n for my big loop. Doesn't really matter because as soon as this line is done, I could use n again, but to be safe, let's do another one. So now create list of numbers from 1 to n. All right, so now we have our main loop. So for n equals 1, n less than or equal to num, n plus plus, and then we'll have the begin and the end. End of n loop. All right. So now we need to calculate a derangement. Or we need to calculate a permutation and see if it's a derangement. Yes?
You could go through all of them and see if their list index is the same as like the
Yeah, so what we can do is once we have our permutation, is we can just go through and check and see one at a time, are they the same? And if we wanted to, we could actually abort the calculation as soon as we see that one number hasn't moved. So how would we generate a random permutation? Yes?
You can do a random sample.
Yeah, that's the command I was forgetting earlier today, but now that I've just done it again, it's much easier to remember. So take a random sample of our list and of size. And now we'll say deranged would be 0. And then for k equals 1, k less than or equal to size, k plus plus, if if deranged k equals what? If we want to see if it's a derangement, what should deranged k equal? It should be k, right? The whole point is to have a number that doesn't move. So if the kth place is still the value k, then we have a derangement. Oh, I'm sorry. It's not called deranged. It's called, we need to give this a list, permuted list. Sorry, so we'll call that permuted list. And so then if permuted list at k equals that, then we'll say deranged equals deranged plus 1. All right, so let's check and see if this does what we want. We have a list of numbers from 1 to size, and that's fixed. And then for number going from 1 to num, we randomly sample from this list something of the same size. Okay, so that's a random permutation. And then we initialize deranged to be 0, and then we go through, and if we ever find a number that hasn't moved, we say we have a derangement. Is this code correct, or is there a mistake? Yes, where's the mistake?
Why are we adding one derangement every time we find a thing that hasn't moved?
Good. So the way this is written, this is a very common mistake. The way this is written, every time we find a number that's not moved, we increase the value by 1. So in fact, this would actually give us more information. This would tell us the number of elements that are not moved. And if we want to try to understand what's the distribution of the number of elements that aren't moved, this is great code. And then in the next line, if we want to increase success, I haven't increased success by 1. What I could then do, I could say is, if deranged is greater than 0, then success equals success plus 1. So this is calculating more information than we need. Right? All we needed to do is we could have just said deranged equals 1, and then if deranged equals 1, increase success by 1. So this is a little bit more information than needed. So now count how many numbers did not move. And again, this would be useful if we wanted to do a more detailed analysis, if we want to calculate what's the probability 2 numbers don't move, what's the probability 3 numbers don't move. So should this work? Do we think that this will give us the right answer?
Can we just put deranged superior equal to 1?
I'm sorry?
Can we just put deranged superior equal to 1?
Just delete that and just make it equal to 1?
Yeah.
So we could do that, and that really won't change anything here. Right?
Why?
Well, because if deranged equals deranged plus 1 every time we find a number that doesn't move, then as long as one number is not moved, deranged will be at least 1.
If two numbers are like didn't move,
Then deranged would be
it's
2.
equal to 1. Like if the derangement would then be equal to 1 but 2.
The derangement would then be equal to 2, but on the next line I consider it a success as long as deranged is greater than 0.
Okay.
So this is giving us a slightly more flexible code for later. Yes?
Does mathematica have Boolean values true and false?
It does have Boolean values true and false. So there's a lot more you can do. I'm trying to code the simplest as possible. For those of you who know good programming languages, you would almost never write this like this. How would you write this? Plus plus. You'd write, deranged plus plus to mean increment the value of deranged by 1. I'm trying to just write things a little bit more expansively, but there are definitely a lot of things you could do. All right, so we run it. Do we think this is going to work? Everybody confident? So we'll do derangement. Let's do 100 numbers, so that's a large enough n, and let's do it 1,000 times. So we observed 63.1% and we predicted 36%. Yes?
Well, isn't the derangement when nobody goes back to their original?
Yeah, so we probably coded the wrong thing.
So we're looking at 1 minus.
Exactly. Right. So the prediction is not 100, but actually 100.0 minus this. Right? So we just miscalculated, or I misremembered the theory. We calculated in class the probability, and then we had to subtract that from 1. You've got to be careful. How many people have a dear Aunt Sarah or a dear Aunt Sally in their family? Sometimes you have to excuse her for her behavior, right? Do you remember this? Please excuse my dear Aunt Sarah, Aunt Sally. The order of operations, parentheses, exponents, multiplication, division, addition, subtraction. When you write it like this, Mathematica does the division here first, and then it subtracts. If you want to be safe, it's never a bad idea to just put things in parentheses to be extremely clear. So now if we run this, now we get a pretty good answer. We can bump it up and do it 10,000 times. Extremely good. Do we expect it to be a perfect agreement? No, this is a simulation. But there's another reason why we don't expect it to be a perfect agreement. Yes?
The computer doesn't choose numbers completely randomly.
So there is the fact that the computer does not choose numbers completely randomly, but there's a deeper issue.
We got the 1/e value by doing it in a
Yes, this is prediction in the limit. And so there is an error in truncation. Now, the alternating series we have is involving things, the sum of 1 over k factorial. So if I'm taking my size to be 100, my error term is going to be on the size of 1 over 101 factorial. I'm not really concerned about detecting an error of size 1 over 101 factorial. If our simulations are that accurate, we have access to such incredible computer power. One of my favorite quotes to describe how good quantum mechanics is some of the measurements in quantum mechanics. The level of precision is equivalent to measuring the distance between Los Angeles and Boston to within the thickness of a human hair. And it doesn't even really matter which way you're holding the human hair, if it's this way or if it's the long way. It's a precise measurement. We have an incredible number of digits. And sometimes you actually need that to see the differences. Relativity, you do not see at small depths of decibels. You have to go really deep for the speeds that we commonly see. All right, so this is 3 somewhat different problems. They're related to things we've been doing in class, and they're just showing you how you can quickly get a sense of what the answer is. Tried to show you some of my computer skills. I deliberately did not try to remember what the Mathematica commands were so I could go through the motions of looking things up. I thought I would look them up a little faster than I did. I apologize for that. One thing you have to be careful about is you may be doing your programming in a different environment or a different iteration of the system than another computer that you're used to. I remember years ago I was trying to show my students in differential equations what Mathematica could do, and it didn't work. And then I realized, oh, the version of Mathematica I have on my laptop is better than the version of Mathematica we have in the classrooms. And the command I wanted to use does not exist on that earlier version. You also have to be extremely careful whenever you do anything in computers that you can trust the output. How do we know random sample really samples randomly? This is black box coding. We can't open it up and see what Mathematica's algorithm is. So there's a huge movement by many people for open source coding, where they want everything to be available so that if you wanted to, you could look up and you could see what algorithm is Mathematica using for random sample. Why might companies not want things to be open source?
Because then you can steal their intellectual
Yeah, then you can steal their intellectual property. They spend a lot of time coming up with really good algorithms. They don't want to necessarily give them away for free. So, especially for some things in linear programming, in operations research, there is enormous amount of money to be made from being able to do things faster than everyone else. And so you do want to have proprietary software. For a lot of things in academia, we like things to be open source. We like to be able to know what's going on so we can trust things. If you can do small cases by hand as a check, that's great. There's something else we could do. And we've got about 3 minutes left, so I'm going to just modify this command a little bit. And I'm going to add a new variable. I love this variable. It's called print. And I will choose the value I want print to be. And depending on the level of print, I can print out different things. So what I will do is the following. I will say if n is less than or equal to 5 and, so the double ampersand means and, print equals 1, then what I want to do is I want to print out the hand. And so this way I can actually see what my hand looks like. And so now what I have to do is I have to now tweak this, and I'll put in a print value. And so now here's my first couple. If I wanted to, maybe I'll do it up to 20. Well, no, it doesn't really matter because we're not going to see anything. But we can see, okay, we've got one king here, one queen, a queen and a king, almost made it. Well, halfway there, I guess. But so this is a way to just check and see what does the output look like. I strongly urge you to do that. Either in your main code or in a separate place, do some runs and make sure that you understand the codes. So over here, let's see, I think I killed this one. So over here, we were just doing some tests of random sample. Okay, yes, it's looking the right thing. When we did random integer, we did tests of random integer. It's very easy to have a slight misunderstanding of how some of these functions work, especially if you use lots of different coding environments. Test, look at the output. Now, if we did the other one where we actually got a lot of kings, so I want to go up over here. So if I now comment this one out and bring this one back into play, if I now do 10, this would be at least one king, right? And so now if I run the code, I'm beginning to see a huge amount, and I can check and see. So what I could have done is maybe I would do 5 times. Oh, no kings. Do it again. 1 king, 20%. Good. So this is a way to just check and see is my code working. All right. Any questions? So you are all adults. I trust you to go through and do however much coding you need so that you feel comfortable doing stuff at this level. I'm not going to ask you to do things more involved than this in the semester. So you can choose how many problems you want to do. If you have any questions, you can shoot me emails, talk to the TAs, but this is really a skill I want you to master. All right.